Gravity is indeed a real force, but not in the traditional sense. In other words, gravity is not a direct classical action at a distance force between two objects. However, in the broader sense, gravity is indeed a force because it describes the resulting interaction between two masses. One of the most exciting areas of research is the quest for a unified theory that combines general relativity with quantum mechanics. Gravitational effects are fundamentally caused by the warping of spacetime and the motion of objects through the warped spacetime. However, the end result is as if a force was applied. Therefore, the most accurate approach would be to call gravity an emergent force, meaning that what looks like a direct force is actually emerging from more fundamental effects, the warping of spacetime. With this in mind, it is perfectly reasonable to call gravity a real force. Interestingly, all of the fundamental forces are actually emergent forces and not classical, action at a distance forces. If you insist on calling gravity not a real force, then you must call all of the fundamental forces not real forces. Some scientists think that even calling gravity, electromagnetism and so forth emergent forces can be misleading because it makes people think of action at a distance forces. They prefer to avoid the word force entirely and instead prefer the name interaction. While Einstein's theory of general relativity explains gravity on a large scale, it doesn't mesh well with quantum mechanics, which governs the microscopic world of particles. Albert Einstein proposed that gravity isn't merely a force between masses, as Newton suggested, but rather a curvature in the fabric of spacetime caused by mass and energy. This is a simplified way to understand how massive objects like stars and planets warp spacetime, creating the gravitational effects we experience. Einstein's field equations, which form the core of general relativity, describe how matter and energy influence this curvature. These equations are complex, involving tensors and differential geometry, but their implications are profound. One key prediction of general relativity is the bending of light around massive objects known as gravitational lensing. This phenomenon has been observed in numerous astronomical events, providing strong evidence for Einstein's theory. Another fascinating prediction is the existence of black holes. According to general relativity, if a massive star collapses under its own gravity, it can form a singularity, a point where spacetime curvature becomes infinite. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. General relativity also predicts the expansion of the universe. Einstein initially introduced a cosmological constant to allow for a static universe, but later the discovery of cosmic expansion by Edwin Hubble led to the realization that the universe is dynamic, constantly stretching the fabric of space-time. Perhaps one of the most celebrated confirmations of general relativity came during a solar eclipse in 1919. British astronomer Sir Arthur Eddington observed the deflection of starlight by the sun's gravity, providing empirical support for Einstein's theory. Before Einstein revolutionized our understanding of gravity, in the late 17th century, Sir Isaac Newton formulated the law of universal gravitation, which fundamentally changed the way we perceive the universe. According to Newton, gravity is a force of attraction that acts between any two masses. This force is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. In simpler terms, the larger and closer two objects are, the stronger the gravitational pull between them. Newton's inspiration came from a rather famous anecdote involving a falling apple. Observing an apple fall from a tree, Newton wondered if the same force pulling the apple to the ground could also be responsible for the motion of the moon around the Earth. This led him to the profound realization that the same gravitational force governs both terrestrial and celestial phenomena. It allowed scientists to calculate the orbits of planets around the sun and understand the gravitational interactions within our solar system with remarkable accuracy. One of the most significant applications of Newton's law was in explaining the elliptical orbits of planets, as described by Johannes Kepler. Newton's work didn't stop there. He also made significant contributions to our understanding of tides. He explained that the gravitational pull of the moon and the sun on Earth's oceans causes the rise and fall of tides. While Einstein's theory of general relativity later refined our understanding of gravity, Newton's laws remain incredibly useful and accurate for most practical purposes. In conclusion, gravity is so much more than that. Let's break it down. Gravity is a force of attraction between two masses. The more massive an object, the stronger its gravitational pull. It was first described by Sir Isaac Newton in the 17th century, who famously had an apple fall on his head. According to his law of universal gravitation, every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. But Newton's explanation was just the beginning. Fast forward to the early 20th century, when Albert Einstein came along with his theory of general relativity. Einstein proposed that gravity isn't just a force but rather a curvature in space-time caused by mass. Now, why is gravity so important? For one, it's what keeps our planet orbiting the sun, making life on Earth possible. Without gravity, we'd be drifting aimlessly through space. Gravity also plays a crucial role in the formation of planets, stars, and galaxies. When dust and gas clump together under gravity's influence, they form celestial bodies. But gravity isn't just about keeping things together. It also governs how these bodies interact. And let's not forget black holes, one of the most extreme gravitational phenomena. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. So next time you drop something, remember there's a whole universe of understanding behind that simple act. Gravity isn't just a force, it's a fundamental aspect of how our universe works.